this video, we'll discuss augmented Dickey-Fuller test of non-stationarity, which is useful when the errors are serially autocorrelated or there is some kind of serial autocorrelation in the data. Let us go back to our simple Dickey-Fuller model, which appeared like this: delta y2 in a simple form, psi times yt minus 1. Then you may have a drift and a trend plus error term. In this model, the idea was that the null of unit root or non-stationarity will be rejected in favor of a stationary process or stationary alternative, which means psi is less than 0 if this test is static. Tau, what we called as tau, is more negative as compared to our critical values or tau critical. So in terms of magnitude, if tau observed or tau from sample is greater than tau critical, then we would have rejected the null of non-stationarity and said the process is stationary. However, for this kind of model to work efficiently, it is required that mu t here, this mu t error term, is a white noise process, white noise IID process. But if there is some kind of autocorrelation structure in delta yt process, which is the dependent variable here, then, and if that is not well taken care of, then mu t's will also be autocorrelated. And if the mu t is autocorrelated, then the inferences and in fact our testing of this, the significance of this psi variable would be inefficient and incorrect. The solution here is to augment this model with lags of delta yt, that is delta yt minus 1, delta yt minus 2 and so on, certain number of, let's say, p lags of this dependent variable delta yt, which will soak up this autocorrelation existing in the delta yt process. Let us discuss this in more detail. So the idea here is to augment the model with p additional lags. Notice this. So we are introducing these 1 to p additional lags in the original model. You can, here we are not showing the drift and time trend, you can add them here if needed, but more importantly we are adding the lags of this dependent variable. The idea is that these lags will soak up additional autocorrelation in this delta yt time series process, and this kind of model which is augmented with the lags of the dependent variable is called augmented Dickey-Fuller or ADF test, and these lags will help us absorb any serial correlation so that our yt will be, our mu t, the error terms would be more cleaner and closer to white noise IID process. Now there's a problem because we are introducing more lags. The number of lags should be very clear. How many lags we are going to choose, that should be an optimum number. There are two ways to choose it, either through the information criteria such as AIC, BIC criteria that we discussed in the previous videos, or through practice, knowing what is the information structure in the data. For example, let's say we are looking at data or financial markets process where 5-week trading is going on, then a lag of 4 to 5 days is sufficient to reflect or capture all the information assimilation process in the market. So it depends on your idea of the market and various practical aspects to choose the lag selection. Why this is important? For example, if you are choosing two less, very small number of lags, then the entire serial correlation that we want to absorb in this delta yt process will not be absorbed, and still mu t will be autocorrelated. If you are using too many lags, it may absorb the autocorrelation, a very large number of lags, but again it will require more parameters, more alpha is to be estimated, and this kind of unparsimonious or non-parsimonious model will introduce noise in the model, and it soaks up a lot of degrees of freedom, that is number of observations or sort of leverage available to you, the number of observations to estimate the model, that is called degrees of freedom, and that will be soaked up, absorbed by these new parameters, and essentially it will result in higher standard errors of estimates and a poor model estimation. So there is a trade-off whether you are choosing too less number of lags or too many. So you need to choose optimum number of lags, and then you run your augmented Dickey-Fuller test of non-stationarity. Again, similar to augmented Dickey-Fuller test, there are other tests such as Phillips-Perron and KPSS test. Though mathematics is not important, but in subsequent videos we'll discuss how to use all these tests in a more efficient way to arrive at accurate conclusion. In this video, we'll discuss the approach to test for non-stationarity with the help of multiple tests of stationarity and unit root tests. Recall, previously we have discussed augmented Dickey-Fuller test, which was essentially a unit root test with its null hypothesis H0 of being non-stationarity y alternate if the null is rejected is of stationarity. Another test, Phillips-Perron, also has a similar null of non-stationarity, and while rejection of null, that is alternate hypothesis, leads to stationarity of the process. In contrast, there are tests of stationarity like KPSS test, where null hypothesis is of process being stationary, while rejection of null would suggest process being non-stationary. Therefore, if you put such tests together and look for the outcome, then ADF-PP test would give you outcomes such as rejection of H0, and KPSS do not reject H0, which are aligned to each other. So you have 2 cross 2 outcomes, rejection and non-rejection. 4 such outcomes with combinations of ADF-PP giving you rejection, no rejection, rejection, no rejection. Similarly, KPS giving you no rejection, rejection, and so on. Now, how to go about it? The approach here is called confirmatory analysis, where you look for evidence which is consistent with each other. For example, rejection of H0 and not rejection of H0 in KPSS, both these outcomes are consistent with each other. Similarly, do not reject H0 for ADF-PP and reject H0 are sort of consistent with each other, because they both tell you the same thing, to take process as non-stationary, while the upper one will take process as stationary. However, if you look at outcome 3 and 4, reject H0 and reject H0, their H0 being opposite, this is a contradictory evidence. Similarly, if you look at this, do not reject H0, do not reject H0, this is also contradictory evidence. So in case your results appear to be from 1 or 2, you have a very solid and robust evidence where all the tests are converging with each other. So to summarize this video, we discussed the approach to test for non-stationarity with using multiple tests, which include 2 classes of tests. One class which is called unitary root test, where the null hypothesis is non-stationary and alternate is stationary, and another set of tests called test of stationarity, where null is stationary and alternate is non-stationary. In this video, we'll introduce a very fundamental and important concept called co-integration and mean reversion in time series properties. To begin with, if two series, let's say yt and xt, have a property of coming together towards each other, and even if in the short term if there are deviations, but they come together towards each other, that means if you take some combination of yt and xt, and because of this fundamental property of staying with each other, the combination of these two series has some kind of long run mean value. And like I said, this long term relationship or mean is driven by some fundamental factor. Let me give you 2 examples. Think of a cash, that is equity, and futures prices of a same underlying, let's say a stock of company ABC. So ABC stock and future, obviously they will not deviate too much away. In short term, they may move a little bit away, but in long term, they should come together. So if I were to take the difference of ABC's cash equity and futures, the difference would remain somewhere around its long-term value, even though on per se ABC equity price may move much up above, and same about future, it may also move much above or down. But if you look at the difference of these values, it will remain closer to some long-term average. Why? Because if the difference deviates, arbitrage, what we call as forces of market efficiency or arbitragers, they will conduct buying and selling activity which will align these prices together, because they are driven by the same underlying fundamental security. And therefore the combination of these two series yt and xt, these two time series, will be stationary even though on their own they may not be stationary. For example, often it has been found that prices are I1. Prices are sort of I1 process, that is integrated of order 1, and that is they are non-stationary on their own. So you need to take first differences like compute returns. Returns is also form of first differencing. So you have to compute returns or take first differences to make them stationary. However, when we look at prices of cash equity of the same underlying ABC stock and futures and take the difference of cash and future, the resulting series would be stationary in itself. And this stationarity property results from the fact that these two series, the cash and future, are co-integrated. Similarly, think of ask and bid prices of a stock XYZ. Now this gap is called spread, and it cannot increase infinitely. Why? Because there are forces of arbitrage. For example, if ask price go much above as compared to bid, then arbitrageurs may and similarly bid price may go too low, then arbitrageurs will take their action, and therefore this gap they will start buying or selling depending upon if it is overvalued or undervalued. They will start buying or selling, and therefore if the gap in ask and bid is too high, it will be driven back to its some kind of long-term mean by these arbitrageurs, so it cannot increase infinitely, and this difference between ask minus bid will remain somewhere in a close range. Even though on their own ask and bid can increase a lot and come down as well, but their difference, the gap between them, will not increase too much. It may deviate in short term, but in long term it will remain at some kind of stationary level. And this is called co-integration between ask and bid, which is driven by some kind of fundamental relationship between these two time series. Particularly in this case, because they are ask and bid prices of the same security, they will be aligned to each other. That means their combination, which in this case is the difference between ask and bid, combination can be in any form. A linear combination can be in any form. In this particular case, it will be the difference which is stationary. Let us look at the mathematical notations and understand the concept of co-integration in more detail. Consider two or series of more variables that are I1 in nature. Their linear combination, or rather what we call as error term. For example, if one series is yt and other series xt, and you express their linear combination as yt plus alpha t, yt as into alpha xt equal to mu t. So mu t is a linear combination of these. You can think of it as an error term or residual or some linear combination of these. There exists some linear combination for a given value of alpha. This mu t will also be I1. So the idea here is that if you combine two or more time series variables with different orders of integration id, if you combine them, the combination term, that is mu t, will be integrator of order d, where integration of order d is the maximum integration. So for example, if you have n variables like y1, y2 and so on up till y1, so these are individually time series variables on their own, different variables, and if you combine them, and let's say the highest order, some of them are integrator of order 1, some of them are integrator of order 2, and one of them, the highest order of integration, is order of d, that is maximum integration, which is of order d, then the resulting error term is expected to be integrated of the largest order, that is d. So the mu t will be integrated of order d, which is the largest order of integration across all these variables. For example, let's take variable y1, x1, x2 and think of a model like this: y1 equal to alpha naught, alpha 1 x1 plus alpha 2 x2 plus this error term. I can express mu t alternatively as a combination of these three variables, y1, x1, x2. Then whatever is the order of integration, y1, x1, x2, mu t's order of integration will be same as the maximum order of integration across these three processes. For example, if y1 is order of integrated 1, x1 is of 2 and x2 is of 3, then in general mu t is expected to be of integrated of order 3. Similarly, if all of them y1, x1, x2 are integrated of order 1, then chances are that error will be of order 1. However, it is desirable to have an error term that is order of 0. And in case in that model that we express that y1 plus alpha 1 x1 plus alpha 2 x2 is mu t, if mu t is found to be I0, if you find that mu t is I0, then this is called co-integration. That means y1, x1 and x2 are co-integrated with each other. What could be those economic and financial scenarios and influences that will lead to I0? And that is called co-integration. So if a set of variables are co-integrated, only and only you can find a linear combination like this. There can be more such variables where you can find a linear combination resulting in a mu t, which is integration of order 0. Integrated of order 0, that means it is stationary, and this is called stationarity. This will result in a property called co-integration across all these variables. In finance and economics, many time series variables such as spot and futures rate, exchange rates, and like I said, bid ask spread, which is the gap in ask and bid, or rather a linear combination of ask and bid, is found to be stationary in finance and economics. The idea is that such series where there's some fundamental economic and financial relationship, in short term, temporary disturbances. In short term, temporary disturbances can make them go apart, but because of these fundamental influences that are providing that structural relationship, in the long run, these fundamental structural forces or the fundamental relationship will bring them together. For example, ask minus bid. It cannot increase infinitely. It has to be range bound. Similarly, cash equity minus future. The gap cannot increase infinitely. It has to be a range bound. And this kind of long-term equilibrium phenomena is called co-integration, which reflects some kind of fundamental structural relationship between time series variables. There can be 2, 3 or more variables, and if we found their linear combination, which we are calling as mu-t or error term, to be stationary or I0, then these variables would be called as co-integrated. So to summarize, in this video, we understood the concept of co-integration. We said that if because of some fundamental relationship, structural relationship, if a set of time series variables, irrespective of the fact that their order of integration is more than 0, order of integration can be 1, 2, 3, but their linear combination results in a error term which has a order of integration I0, which is stationary, then these variables are called co-integrated variables, and this co-integration results from some kind of fundamental economic and finance relationship. In this video, we'll introduce the error correction models, or also referred to as equilibrium correction models. Typically, when you are dealing with univariate series individually, then a good approach to deal with non-stationary or integrated series is to convert them to I0. For example, if it is I1, you take first differences and convert them to I0. Generally, when we are talking about financial economic series, we are talking about stochastic non-stationarity. So in this manner, when we construct I0 series, often when you are looking at some kind of time series models of a multivariate nature, then also you can follow this approach while converting individual series at I0 level and then try to find this relationship. But there is a problem, as we'll see in the next discussion. This kind of approach where we convert a series such as I1 to I0 and then estimate the relationship between, let's say, a series like YT, XT or so on, then we lose the long run relationship between these variables. This we'll discuss shortly. But why are we discussing only I1? Why not I2, I3 and so on? Generally, in finance and economics, we do not have series like I1. For example, prices would be generally I1, or similarly other series such as GDP and other things would be I1. You convert them into I0 by taking a log return kind of form. So when you convert them into first difference or return form, they become I0. Now, let's say if there are two series YT and XT, they are I1 of nature, and you try to estimate a relationship which is changes in YT vis-a-vis changes in XT, and try to estimate this relationship. For example, you may have cash or future data and you convert them into their first differences or return forms. The problem is that this is sort of short-term relationship. Why? Generally, when you're talking about long-term relationship between two series YT and XT, in the long run, these variables, they approach some kind of steady state equilibrium. What do we mean by steady state equilibrium? A state where YT is not changing much because it has reached its equilibrium value. The difference between YT and YT minus 1, which is delta Y, is approaching 0. That means there is some Y steady state value which is approached in long run, and therefore time by time there are no changes. So delta YT is approaching 0. And same for XT. As XT approaches its equilibrium level, delta XT also approaches 0. So they are approaching some kind of steady state, long-term steady state value. And therefore delta YT and delta XT are not changing, becoming close to 0. So if you want to estimate this kind of relationship, that becomes meaningless, because then it has no solution, because this delta YT and delta XT, not only they are not changing, they are close to 0. So there is no solution to such problem. However, there is one solution to this problem where you can get not only the short term but long term solution also, only and only if the variables are co-integrated. Let us see how. The idea here is that if two series such as YT and XT are co-integrated, then we can combine their lagged values and their first differences to find this kind of model, which is a combination of this first component short term and also their lagged values, which essentially captures their long-term relationship. So if they are co-integrated, we can say that there exists a combination like this, which is a long-term relationship. I repeat, so if we assume that yt minus 1 and xt minus 1 are co-integrated, there exists a long-term relationship expressed in the form of this, which is essentially nothing but the error term et, which reflects the deviations. This et reflects deviations in their equilibrium levels. So this component is put here and the short-term relationship is captured here. So essentially what we are trying to determine through this relationship is what factors drive changes in yt, and these are not only changes in xt but also deviations from long-term equilibrium relationship captured by this et or this linear combination. And assuming that there exists some linear combination, because this yt and xt are co-integrated, this et would not be of order I1 or higher if even if yt and xt are integrated, but it will be I0 because of the co-integrated relationship. And this is what we call as error correction model ECM or vector error correction model VECM, or often referred to as equilibrium correction model. In this model, as we discussed, this yt minus 1 minus gamma times xt minus 1 is the error correction term et, which captures the deviations from the long-term relationship. So this term gives you the deviations from long-term relationship, and this is supposed to be I0 because of the co-integration, even though yt xt are I1 or maybe higher also. Also for modeling perspective, you can also have a constant term like alpha here. You can, in this relationship also, you can have some kind of constant if required. And because this entire relationship is purely stationary, why? Because this relationship is I0 and this is anyway I0. Therefore, it is perfectly valid to use OLS procedure here. So in this relationship where we are saying that changes in yt are a function of changes in xt plus some kind of, let's call this term coefficient beta 1, and another coefficient beta 2 which captures the relationship between xt plus some kind of error term. Let us interpret this one by one. First and foremost, here in this short-term error correction term et, this is appearing with the subscript t minus 1 because it indicates deviations from equilibrium in the previous period. So the current changes in delta yt which come with the subscript t are affected by the previous deviations from this long-term equilibrium relationship. So there we need a subscript t minus 1. That means changes at time t are driven by equilibrium deviations at t minus 1. That is logical. Second, you have a gamma coefficient here which captures sort of long relationship between yt and xt minus 1. Obviously, depending upon sign, you can get the impression about relationship, but the magnitude of this coefficient gives you the long-term relationship between x and y. Next, you have beta 1 as a coefficient of delta xt. Because this is a coefficient of changes in xt, it sort of captures the short-term relationship between delta yt and xt. So because we are using first differences here, again the assumption is that this yt and xt are I1. Generally series in price series and other economic and financial series are I1 in nature, and their first differences are I0. Generally that is conventionally that happens. Next, this beta 2, which is the multiple of this error term or this long-term relationship deviations from the long-term relationship, is called as speed of adjustment because it is the magnitude of this term essentially reflects how much error in the previous period, which was ET or deviation from the equilibrium, was corrected in the current period. So it sort of gives you the correction in error or adjustment towards the equilibrium level. So this beta 2 measures that adjustment towards the equilibrium or that speed of adjustment towards the equilibrium. Now, just to summarize this discussion, here we use for two series. This can be extended for a multiple series, and where we can use a larger co-integrating vector with multiple variables, such as you can have a vector like yt plus alpha 1 x1t plus alpha 2 x2t and so on. This is called co-integrating vector, where instead of only having two variables, you can have more variables. So if you have a relationship like this, yt plus alpha 1t xt and so on plus alpha 2 x2t and so on, the co-integrating vector can be represented as 1 plus alpha 1t plus alpha 2t. So it's just a vector of coefficients. This is called co-integrating vector. To summarize this video, we said that often the approach to deal with non-stationary relationships or sort of multivariate non-stationary relationships is to take changes, differences in the variables or series and take them to I0 level. And once you have those variables at I0 level, then try to find some relationship if that exists. However, the problem with this kind of approach is that it only captures short-term relationship, and if there exists some short-term long-term relationship and the variables are equilibrium, such approach may lead to problematic results. So only and only if a system of variables is co-integrated, then only there exists a modeling approach called error correction models, where we use a combination of first differences or I at change level, first differences or change levels I zeros, plus the long-term relationship which is co-integrated, which is in the form of lagged variables, and combine them to get a class of family of models called error correction models. This kind of approach helps not only estimate the long-term relationship, short-term relationship, but also adjustment towards equilibrium as time progresses. However, this approach can be only applied if the system of variables or the system of linear combination of these variables is co-integrated, that is driven by some kind of fundamental long-term relationship. In this video, we'll discuss the Engel-Granger approach to co-integration and error correction model. So what is the intuition here behind the Engel-Granger approach? Recall, if a set of variables such as yt, x2t, x3t and so on up till xkt are co-integrated. So you have k variables that are co-integrated. So a system of variables with co-integrated values. This model represents a sort of equilibrium where mu t can be I0. It can be I0 only if these set of k variables are co-integrated, and therefore we can find a linear combination of these variables which is mu t, which can be I0. And then all you need to do is set up test of stationarity on mu t to confirm this. And that is what lies behind the Engel-Granger approach, as we are going to see. The two-step Engel-Granger approach to co-integration and error correction model is as follows. In the first step, we proceed with the variables such as yt, x1t, x2t in their original I1 form, assuming these are financial and economics variables, so they would be I1 nature. Then in this model, let's say model like yt equal to beta 2 x2t plus beta 3 x3t and so on up till beta k xkt. In this kind of model, we estimate the residuals from this model, that is mu t. At this stage, because this relationship not necessarily be co-integrated, we cannot say anything about the hypothesis behind beta, beta 3 and beta k and their statistical significance. So the next step would be to test these mu t's, the error terms, for their stationarity or whether they are I0 or not through tests such as ADF test, TP test and KPSS test, as we discussed earlier. In the next step, we approach the next step only if the residuals are stationary. If you find that residuals are not stationary, indeed they are I1, then you have to only find the short-term relationship by estimating the first differences in yt, delta yt, delta xt and so on. So you have to find the first differences, and that only short-term relationship will exist. However, if you find that mu t's are stationary, then you can approach with the VECM, or what we call as error correction model, which is a combination of these changes in delta yt and a short-term relationship represented by this delta xt along with alpha 1 and mu t, which is the error correction term. Now please note, delta xt need not be only one variable, it can be a system of variables such as delta xt, x1t, delta x2t and so on, multiple such variables it can have. And the second term, which is mu t, represents that long-term relationship such as we discussed earlier. For example, it can be yt minus 1. We are using t minus 1 because it represents values at lags. Then minus beta 2 x2 t minus 1 minus beta 3 x3 t minus 1 and so on. For example, if this is the nature of relationship as we saw, then your co-integrating vector would be 1 minus beta 2 minus beta 3. You can generalize this relationship for more number of variables, and this captures this mu t. So this is your mu t. When you again estimate this relationship, then in that case alpha 1 captures your short-term relationship, alpha 2 captures your correction in error. It's like speed of adjustment towards equilibrium because it is getting multiplied to mu t, and this is your co-integrating vector 1 minus beta 2 minus beta 3, which captures the long-term relationship. And now this model can be estimated with OLS. However, all those problems that are conventionally associated with OLS, such as autocorrelation, heteroscedasticity and so on, are also applicable here as well. To summarize this video, we discussed the Engel-Grengel two-step approach to estimation of error correction models with co-integrating relationships. In the first step, we found the relationship in the long-term model, and in that long-term relationship, we extracted the residuals and examined them for their stationarity. The ECM kind of model will only exist if these error terms were stationary and I0, and if they were, then we would go ahead with the ECM model, which is a combination of first differences and lag terms of the time series variables. If the error terms are not stationary, then we have to restrict ourselves to only with the short-term relationship. To summarize, in this video we'll recap the time series stationarity properties. We consider a weak stationary process which has a constant mean, constant variance, and a constant autocovariation structure. If a process is non-stationary, any kind of modeling and estimation efforts may result in spurious regressions. There are two kinds of non-stationarities. First, the stochastic non-stationarity resulting from autocorrelation coefficient of 1. This kind of non-stationarity is removed by taking first differences. The process is said to be of order d if it requires first differencing d times. In finance and economics, most of the time we observe stochastic non-stationarity of order 1. The second is due to a time trend in the process. This kind of non-stationarity is dealt by incorporating a time trend in the process and extracting the residuals. When examined visually, a white noise process has no discernible structure and fluctuates around its mean frequently. A random walk process deviates from the mean value and keeps wandering for long times. A random walk process with a drift remains further away from its mean for very long horizons. A deterministic trend process fluctuates around a mean that has a secular increasing or decreasing linear trend with time. Autoregressive processes with zero autocorrelation coefficient behave as white noise processes. As this autocorrelation coefficient approaches 1, the process comes closer to a random walk process. The tests of stationarity are of two kinds. First, the ADF test with a null of non-stationarity, and second, the stationarity test as KPSS test with null of stationarity. Both types of tests are employed in conjunction and their results are used in a complementary manner to make inferences. Often, a system of time series processes is integrated of the order which is the maximum order of integration across all of the components of the system. However, in case this system is co-integrated, then a linear combination exists which is I0, that is integrated of order 0 and stationary. The co-integration in a system of time series reflect some fundamental structural relationship across these time series such as cash equity and futures or bid-ask prices and so on. Therefore, such system has a long-term mean reversion towards which the system reverts over long term. In the short term, the system can deviate from this long-term mean. To model such co-integrating relationships, we employ error correction models or what we call as VECM. These models employ a system of first difference to capture the short-term relation and lag terms in the form of co-integrating vector to capture the long-term relationship. If there is no co-integrating relationship, then only short-term relationship exists. One of the most employed approach to this co-integrating relationship is two-step Engel-Grengel approach. In the first step, we run the long-term model to obtain the error term. These errors are tested for stationarity to confirm the presence of a co-integrating relationship. If found stationary, then this error term captures the long-term co-integrating relationship and is employed along with first differences, short-term model to construct the ECM or VCM model.